In this video we will implement a breadth search with levels, and also we will implement the find shortest path function, or shortest path between two nodes. Okay, what is a breadth search with levels? For example, on this graph we can see that we visit our nodes in this order. We started from A and we go to B and C, and B and C is level 2. A is level 1, we start from 1, and then from B we can go to D and E, and this is a level 3. So, and from every node on level 3 we can go to level 4 nodes, and so on. Okay, how can we do this? We already implement the breadth search in a previous video, you can see it by the link. Now we take this type signature of breadth search and do a little modifications here. At first we will here we have the list of visited nodes, and here our queue, and this is the result. So we need to replace every A with pair of A and int. This int will represent our level. And now let's start the implementation from, I will call this function breadth search with levels. And some corner case here, if we have an empty queue, this means that we need to stop. We have no sequence of our BFS. But if we have BFS with some graph G and visited vertices, and also we have some queue and some elements in our queue, we need to unpattern match this list, and also we need to unpattern match the top element of the list, because now it is contain not only the vertex, it also contain the vertex level. Okay, and we can take this vertex and its level and add it to our result, and we go to recursion from here. We call again with our G, with our visited vertices, V1 I think. We do a little bit modification later for the, and also we increase our queue, adding some pairs node with its levels. I will define A later, and that's main idea. And now let's define the helper functions. First of all, we need to define V1, and they defined our V1. We just add this thing to result, and we need also add this thing to our visited vertices, what we give on input. Now let's define our A. So A, to build A, we need all adjacent vertices of our H vertex, which we extract from the top level of the queue, and we need to extract from subtract from it all the vertices what we visited and what the vertices what in our queue. Okay, and here we have here pairs, and here we have pairs, the vertex and its level, because we have this type signature for our input parameters. And this means that they need to extract the first element in all the cases. And I will do this with some helper function. I will call this AU here and here. And here I need to change this. And let's define our helper function. It's just take some list and it iterate over this list and extract the first element of every pair. Okay. Let's put parentheses here. And next thing which I need to do here, I need to, in this expression, I need to build a list of not visited adjacent vertices, but also I need to add pairs. I need to add the levels to these vertices. And I will do this with added a level function, helper function, and it needs one parameter, it's the level, and this level will be the level of our head element current, which from which we review our adjacent edges, and this level will be incremented by 1. Okay, because we on every iteration increase our level by 1. So, and let's define this helper function. It takes some list of vertices and level, and it's also produce from our list of vertices. We produce a pair of our vertex and level. Okay, I think this should work. Let's check this. Okay, it's compiled without errors, and we can try to run. Let's run our BFS, the levels. So we need to provide a graph. We have some graph here. Such a list of pairs between these vertices, and we run our BFS on this graph. Of course, we have at first step we have no visited vertices, and we need to provide a first pair for our queue. It's for example, I can take a vertex and its level, start level will be 0. Okay, and we can run it. So, and you can see that we built our levels. Our A has 0 level, B, C, and X have level number 1 because we can. It's adjacent to A to B, A to C, and A to X are adjacent. And then we can the Z have level 2 because it's adjacent to C with level 1. Okay. And now let's build a function which build all the shortest path between two nodes. So I will call this function SPS paths, and its type signature is look like this. It takes some graph of type A, some started vertex A of type A, some final vertex of type A, and it produce maybe a list of all paths. Okay. Maybe because if we provide the vertex that not exist in the graph, we will return nothing. Okay, and let's start from implementation. We have a graph G, we have start vertex A and end vertex B. And we will use do notation, we in maybe monad. First thing we need to do is to check that our vertices in our graph. Okay, we will use BFS function for this. BFS, of course, with levels. We will use this levels information to build these paths. And now at first let's build some helper function here for our BFSL with the different type signature. It will just use our BFS underscore L. I will call this function BFSL. It takes some graph and takes some started vertex, and it's do initialization of the BFS subscribe L. Okay. We run our BFSL function with this graph G with the empty vertices at start visited, and now we need to check is our vertex V in our graph. And if it is not in this graph, this means that we need to remove we need to return an empty list. Okay, let's write this condition. If lm our vertex v contain in vertices is a function which returns the list of all the vertices of our graph G, and we check that our starting point V presented in our list of all vertices. And if this happens, that's okay. We can continue our algorithm and we start from the V and 0. Okay, otherwise we return an empty list. Okay. Okay, we will provide this empty list to our BFS subscribe L, and it will return an empty list. So let's try to recompile some errors here. Of course, I need to add the brace here. Okay, and here as paths. So we can continue to implement our function. So we at first they need to use this function lookup to check. Okay, they will use BFSL search. So let's look again how our result of BFSL looks like. You can see that they have a list of pairs. So we have some function that's called lookup, which takes some element of the, if they have a list of pairs, and the first element is used as somehow like an index, we can search for by this index, and if it present, we return maybe B. We return just B. So, and this function, I can check that our vertex A in our BFS. Okay, by BFS I mean with BFSL, and I will define it later. And also I need to look up this pair for vertex B, and take its level to name it with name LB. Okay, now we have a level of the vertex B using our BFS. So let's do the definition of our BFS here. BFS is BFSL. BFS with levels of our graph G and started from vertex A. And then we need to return a list of lists. And to define this list, I will use path function, which takes started vertex A and final vertex B with its level LB. So now let's define this path function. I will unpattern match this pair, and here I need some guards. So if our A equal to B, if we want to find a path from the point to itself, this means that this path consists only from a list of with one element, this A. Okay. So actually not list, a list of lists. So we need to find all paths, and that's why we need a list of lists. And let's rename this function with PS here. PS, I mean paths. And other guard is if A not equal to B. This means that we need to okay, here we need to implement some complex expression, but I try to explain it's as simple as possible. Okay, we have okay, imagine that we have 2 points. So one point is B and one point is A. We want to find all the paths from A to B. We know the B vertex, and they know its level. At first step, they need to take all the adjacent to node B vertices with level LB minus 1, because we go one step closer to our A, and we can do it with vertices on the level minus 1 of the vertex B. This is the first thing what we need to do. So we can take this with our adjacent function, which takes some B, vertex B, and also we can't use adjacent. We need some helper which take this vertex B and its level, and this helper will return all these adjacent vertices, okay, on the previous level. This is the first step, and then they get the list of these adjacent vertices. The next thing they need to do is to find all the paths from all these vertices to our started vertex A. And they can do this using fmap. We've partially apply our PS, so we go to recursion here, and we put partially apply the first vertex, and the second vertex will be every element of this list. So every adjacent to B vertex with the level minus 1. And here, using this expression, we will get a list of lists. Okay? And then we have this. The next step, we need to concatenate all these lists to get all the paths. But this is very important, that this will be not from paths from B. This will be all the paths from the adjacent there's to B vertices. And we need to add them, concatenate. With the list concatenation, we will use false for this if they have list of lists, and start from empty list. So now we have all these paths, and to transfer them to real paths from B to A, we need just add B with fmap to them. Okay. And this will give us the solution. Next step we need to do is to define this adjacent underscore function. Okay, adjacent underscore, it takes some vertex B and its level. And we need to find all the adjacent vertices. So how we can find them? We have function adjacent, which take graph G and vertex B. Okay, let's extract every vertex, every adjacent vertex. Okay, but here we need only the vertices of our level LB. LB minus 1, sorry. And we can find them in our BFS. Our BFS is a list of such pairs. We can find we can use find function. Okay, let's look at this signature. So here we need some predicate and a list, the foldable. And let's Let's implement this. So we use find on with some predicate on our BFS. BFS defined like this. And our predicate, of course, the is just equality function partially applied with our vertex v extracted. I need to extract this here, and then partially applied each this pair of the vertex and level -1. The vertices that we're interested in, and find will give us the result. Okay, this I think should work. Yes, I think yes. And of course, we have a list. We will construct a list of maybes, and they need to cut their nothings. We can do this with cut maybes function. Okay. And I think this should work. Let's try to recompile. No errors. Very interesting. Okay, let's run. Let's run all the paths. We have graph G and all shortest path. I want to know all shortest paths for graph G, and we start from A, for example, and to C. Okay, and we have only one shortest path from A to C. And this is correct. But what if we have... Let's do some example when we have more than one shortest paths. How to do this? Okay, we have A to B and B to Z. Let's make A to W and W to Z. Okay, let's try to do this. Where is our graph definition? So here I will add A to W and W to C. Okay. And now let's try to recompile and run. We have such a graph, and we want to from A to C. A from W, W from C. Of course, I need to remove A from C here. On A to Z. Okay, let's remove this. Okay, and now we can see that they have two paths. From A we can go to B and then to C, and also we can go from A to D to C. Let's add some longer path here. For example, what if we go from A to B, and then from B to Z, and then we have this path, and then we go from Z to C. This is a longer path, and it doesn't present it here. So I think this is correct implementation of the shortest path. And of course we can, using this implementation, find only one short path. We can take the head of this just function. Of course, if it contains some string, some path, like this, they can run as paths, and when they are functor, we can apply a head and take only one path. Of course, this is not safe. If they have empty lists, it will crash. But I skip this implementation here. So guys, thanks for watching. This was the level breadth search, the levels, and find shortest path function. Thank you. Push like, push subscribe, and see you in the next video. Bye bye.